My God.
Welcome. Good afternoon. Who am I? My name is Reyansh FPN. I am a senior in this school, Frisco High School. I will be talking about electrical and computer engineering, okay? Motivation. Sometimes life is like a tunnel. You can't always see the light at the end of the tunnel, but if you keep moving, you will come to a better place. What is chip design? Chip design is a bunch of these little transistors connected together to form a delivery system. These are in the form of chips, like they can be called the CPU or the GPU. There's more, but these are just some examples. And basically, they handle inputs and outputs. So if you press your trackpad or the button, what does the chip tell the computer to do? That's kind of what it is. Now I will talk about the essential components of a chip. All right. Transistors. A transistor is a tiny electronic switch that controls the flow of electricity in a circuit. In computers, billions of these transistors are required, and they turn off and on really quickly to get those ones and zeros that you see. That, oh, computers run on ones and zeros. That's kind of what it is. So this allows computers to process and run information pretty quickly. This is called a logic gate. You have your flow, and then depending on what the input is, it'll either say yes or no. It's basically a bunch of true or false things that a transistor is. So it's like, if I'm detecting an input, then yes. If no, then no. You know, like if like AND gates, OR gates, a bunch of these gates. Like, moving on, this is what a transistor looks like. This is from a 1950, taken here in Texas at TI. Texas Instruments made the first transistor ever on Earth. That's pretty cool. Wires. Wires are what connect these transistors together. They're like the delivery man, right? So the packages are like these electric signals, and the delivery men are like the wires taking it from one place to another. This chip that you see is 50 years old, and it's so complicated. It looks so cool, from 1970. In just 20 years, we went from this to this. It's pretty cool. How are chips made? You see, chips require a lot of engineering, and so this is taken from a movie, Spider-Man, Far From Home, or No Way Home, or one of the homes. I don't remember. But this is our wonderful Spider-Man actor, and as you can see, he's working on something with this weird device. Well, this device is called a fabricator. Okay, and this is used to make chips in the Marvel Cinematic Universe. But in real life, they're much bigger than this. It's not that small. So let's get to lithography now. This is the process by which chips are made. Okay, we use extreme ultraviolet lithography as our current process to make our chips. So after a chip is designed by engineers using a software, a process called lithography prints the circuit onto a silicon wafer. And these are not the cookies you eat. Okay? So first we get a bunch of sand, you know? You can go to like San Diego or Galveston, like get a bunch of sand. Then you get the silicon from the sand. And once you have silicon, you kind of like spin it around really fast, and it turns into these cylinders, and you slice it up to make wafers. You print the circuit onto the wafer, and voila, chip. One of these wafers have like a bunch of little squares, if you can see, and each square is a little chip. So one wafer can go for $10,000. Very expensive. So after you have the sand and you make it into silicon, it looks kind of like this. These are the little cylinders I was talking about, and these cylinders are then chopped up to make wafers, silicon wafers. Okay. Now the process of printing a circuit onto these wafers is pretty complicated. This is the most advanced machine created by mankind today. Okay? And last time I talked about this, I believe it was a bit too confusing, so I'll summarize it a bit better. But basically, you have your wafer on the bottom here. Think of it like a printer, right? And instead of ink, we're using light to print onto the wafer. Okay? There's a special coating on these wafers, and the light basically engraves the wafer, and then you put the little metal stuff in so you can form the chip, right? So it starts up with a laser here, and there's like these tin drops, like droplets of tin, and you like shoot it with the laser 3 times, and it becomes plasma, and that goes through these mirrors, and it prints your wonderful chip. So yeah, here's an example. This is like tin that just drops by, and then this laser shoots it a bunch of times, and it turns into plasma, and that's what we call EUV radiation. Extreme ultraviolet radiation is what it stands for. So that's this, and then it goes through these mirrors a bunch. Here, these mirrors, and it prints it onto the wafer down here. I hope that makes sense. The mirrors that the light bounces through is actually the smoothest object on Earth. That's pretty cool to know, right? And here's a little demonstration of how printing looks like. This is from ASML, which is the company that makes these huge fabs. They're like, I think one is probably like a third of this room, so like from here to there. That's how big one of these fabs are. See, like really big. Chip layers. So here is basically how a chip is kind of formed. You got your transistors on the bottom, and then these other layers are like a bunch of wires that just go and connect the transistors together. Okay? Moore's law. Now we're getting into like what my topic will be about. So Moore's law is an observation of the number of transistors on a microchip that will roughly double every 2 years. So that's basically what Moore's law is. Basically, it just means as the chip gets smaller, we're going to have more transistors on the chip. Okay? And the more transistors, the more faster and complex the chip can run information. So, is Moore's law dead? Because like this Moore's law, I think it was made by like some guy at Intel who ran Intel, and he kind of made this little law thing. But it's starting like this basically like this theory is like starting to slow down because many industry experts are saying that Moore's law does not apply to modern chip design due to physical limits, atomical limits, TSM. Due to atomical limits, it's kind of hard to make it smaller and smaller, the chips. And so TSMC, the current leading chip fab, and the only reason the US is still against China taking over Taiwan, is currently under 2 nanometer node, meaning every transistor is spaced 2 nanometers apart. That's like really small. Like you can't even see it. Like if you were to zoom into a chip, it would look like a whole city, you know? While this is impressive, the rate at which nodes are getting smaller is decreasing, and this is bad. That means that Moore's law is not going to be a law. So my goal, I would like to research a new process that can continue Moore's law and even exceed it. Photonic chips. While through my hours and hours of ruthless researching and a bunch of articles, I've figured out what photonic chips are. Instead of using electrons, they use light to perform calculations. These types of processors can provide up to 1,000 times of speed increase and 400 times more energy efficient. And they wouldn't produce any heat because electric chips or electronic chips, you produce heat. These wouldn't produce as much heat because light, well, it's like just very less heat. So we do use photonics in our current day economy. So basically right now what it looks like, it's like, you know, like the Atlantic Ocean, right? So when you call someone from the other side of the world, you call them using this, like these wires that transport your calling to the other side of the world and the other side of the world to here. And so a bunch of light goes through these wires, and it's kind of what, it's not a photonic chip, but it's just how we use photonics right now. So now, as I was beginning to learn more about photonic chips, I was attempting to interview. Now, unfortunately, I didn't get a mentor, but like I did some nice interviews. The first one, Dr. Balakrishna, he has a doctorate in bioengineering at UT Austin. He also taught at UCLA for 10 years, which is insane. So I got like really lucky to interview this guy. He's pretty cracked. Right now he's retired, so like basically unemployed. But we talked about how electric engineers are used to design sensors and amplifiers for tiny biological signals. It's about the ocean, or it was something about the ocean, and like it's pretty cool. He taught me a lot, and I appreciate it. Like he sent me an image for his icon. I didn't get an image from this person, but yeah, he's like really nice. Miss Mogra did her undergrad at NYU, and she was one of my first interview research thingies. I didn't really get much out of it, but we talked about data centers and infrastructure and stuff. So yeah. Mentors, unfortunately, no. I didn't find a mentor, but I researched a lot. So
Dr. Balakrishnan.
Yeah, Dr. Balakrishnan helped me a lot. He pointed me through some like articles and research that he was looking at. So
His son.
I continued. Please
Sorry,
let me talk.
I'll talk later.
Yeah. So I continued on my research, and I learned about waveguides, which is how information, instead of using, because you can't use electric signals in photonics, light travels through waves, right? So detecting like these different waveguides is how you would get the information. And so as I was learning about photonics, I wanted to learn about the current economy of photonics, like what companies are trying to do photonics. I found light matter. There's a couple other ones, but I just use light matter as an example. They're a technology company that develops computer chips which uses light instead of electricity to process and move data. It focuses on building photonic hardware for artificial intelligence. So they're focused on AI, using photonics for AI, where massive amounts of data is needed to transfer quickly between chips. Its technology uses silicon photonics, which is a type of photonics. So basically, it's like photonics on a silicon chip. To increase speed and reduce energy compared to traditional electronic chips. Light matter also creates specialized products like optical interconnects and processors to help build large data centers that run AI models. So like basically a bunch of AI stuff, but they are doing something with photonics that's pretty cool. Now, is photonics viable? Unfortunately, not right now, because our devices all run on electricity. So let me kind of like explain this better. So when you're on your phone, right, you have a screen, and the information is displayed with like light, which you use electricity to like display the light bulb, right? So you would need to convert electric signals to light, then the light will process it, then convert back to electricity if you want to use photonics. Converting electricity light and then light to electricity is slow, and so that's the reason why we can't use photonics right now. But there are companies like Light Matter who are working on reducing that delay. But if we can get that delay like reduced significantly, then photonics could be a viable option for our future in chips. The debate between quantum chips and photonics. I was like, photonics are pretty cool, but like I know that everyone talking about quantum chips and stuff. So what exactly is the difference between quantum chips and photonic chips? Quantum computing and photonic chips are both very advanced technologies, but they solve different problems. Quantum computing uses principles like superposition and entanglement to perform certain calculations much faster than classic computers. Photonic chips based on silicon photonics use light into electricity process and transfer data more efficiently, while quantum computers are powerful for specialized tasks like cryptography and complex simulations. Photonic chips are designed to improve everyday computing, such as AI processing and data transfer. So basically, in short, quantum computing aims to revolutionize how problems are solved, while photonic chips aim to make existing computing faster and more energy efficient. So to summarize that, quantum chips are for big, vague questions. I guess like hacking something, like where you need a bunch of like data. It's more of like big, overarching calculations, while photonic chips are more useful for single step-by-step calculations. So we can use quantum computing, but you're probably never going to have a quantum chip in your phone or computer, because quantum chips will just be used by companies for like bigger questions. But maybe photonics could be used on your phone or computer in the future. So they do solve different problems, so they can be compared, but they're two different hats, I guess. My final product, I attempted to make a brochure explaining the future of photonic chips, kind of like an advertisement with the pros and cons of using this technology. So I started off with, researching and figuring out what I want to do, then brainstorming. Then I started modeling with um, processes or with programs using CAD, and then now I'm going to explain it. So first, I researched how photonic transistors look like. So we know normal transistors, like that diagram I showed you, but this is how a photonic transistor looks like. And so we start off with a laser here, and then these ring resonators, they process the waveguides, and they kind of tell, like, those waveguides I showed earlier, it like kind of shows what information is being transferred. And then these optical modulators, they convert it back into electricity to send it off. You know. So here are my findings. I researched different topics like speed, energy efficiency, heat generation, scalability, reliability, mature technology, cost, best use cases, data transmission, parallel processing, and limitations. And I compared electrical chips, photonic chips, and quantum chips. Okay. So I found that electrical chips are fast but limited by electricity resistance and heat. Photonic chips are very fast because light travels way faster with less resistance. Quantum chips are fast, but like I said, they're solving a different problem. So it's mainly between this and this that we're comparing. But I just included quantum chips just to compare it. Energy efficiency. This one is the most energy efficient. This one can be energy efficient, but only for complex problems. Heat generation, this generates like a lot of heat. This one generates little to none heat. This one is very sensitive to heat, so you have to keep quantum chips in like sub-zero temperatures for them to run. Heat generation, or I talked about that. Scalability, this is highly scalable with our current industry and manufacturing. Like TSMC, a bunch of companies working on electrical chips. This one is still developing, so it's gonna. Yeah, we'll need a lot of investments to scale photonics. This one, it's not very scalable because quantum chips are very unstable. Reliability, this is reliable and stable because of all the years of research we've been doing. This is generally reliable, but it's still like new, and so there's going to be errors. Same with quantum chips. Maturity, very mature, not mature, very not mature. Cost, electric chips are affordable due to our global supply chains. Photonics are expensive because they're using new manufacturing methods, and quantum chips are just unreasonably expensive. Best use cases, everyday computing, high-speed data transfers, and cryptography. So like different ways to use these different chips. Now, how data transfers are slower than photonic chips, and this one is not focused on traditional data transfers. This is just like slow, fast. Okay. Parallel processing. Parallel processing is basically processing information at the same time. For example, say I click a button and I need two things to happen. One part of the chip runs something, another part of the chip runs something else. It's called parallel computing. It's computing at the same time. This one is limited by architecture, so if you design it for parallel computing, then you can have parallel computing. This one, there's a strong potential for parallelism because you know how I said light runs on waveguides or whatever? So traditional electrical chips, they use analog systems. This one, it's more like waveguides. So you can have like 1.00158 as your answer. This one is just ones and zeros. So you can have a lot more complex information processed by light. So that's pretty cool. Limitations, heat and power, and then limitation photonics are just integration right now. So, do we have any questions while I'm wrapping up my presentation? No? Okay. Hopefully, you guys learned a lot. Thank you for listening to my amazing presentation. I spent a lot of time on this, so I hope you memorize something to tell to your parents at home. So, bye-bye, and please clap very loudly. Thank you.
You guys have any questions?
Yeah. Or like I had like a question I didn't want to ask you on this video.
Yeah, go ahead.
Let us stop the video.
What's your question?
It was just that it was more like advice. Like